Good afternoon, everybody. My name is Mamujakile Sole, and I am a Prokon technical consultant with micrographics, and welcome to today's webinar. Please note that if you do have any questions for me for today's webinar, do leave all the questions on the chat for today, and I will definitely be able to answer all the questions while we finish on today's webinar, or while I do finish with my webinar for today, and I will definitely get into that. And yeah, let's, without wasting any time, let me get back or let me start or begin with my webinar. And on today's webinar, I will be creating a slab on elastic foundation with Prokon frame analysis. And my agenda goes as follows, or this is what I have in store for my webinar. On my agenda today, I will be firstly, I'll start by introducing introduction to spring elements in frame analysis, and secondly, I will be creating notes because we know that Prokon frame is definitely nodal based, and before you can create any model in frame, you need to create your note. So that is the first step into creating the model that we will be looking at today. And thirdly, we will be populating our shells for the slab that we will be having. And fourth, we will be inputting or doing a spring element input, where we will define all our springs that we will have in our model today. And then from there, we will add in supports just to provide lateral stability in our model, because we know if you try and analyze a model that is not even stable at all, the program will definitely flag it and actually tell you that you need to provide stability in your model. And then we will be assigning loads to the slab, meaning we will apply any dead load, any live load to our slab if needs be. And then from there, once we're done with modeling, we'll definitely run an analysis to look at or assess the outputs that we might get from this specific model that we will be building today. And then lastly, on our agenda for today, we will definitely look into conclusion, where it is a Q&A session where you guys can definitely ask questions. But like I said, you can definitely put all your questions on the chat if you have any questions as I'm proceeding with building our model for today, and I will definitely answer all the questions that you might have as we proceed today. Right. So without wasting any time, let me start with the introduction to spring elements. So the first thing is spring elements act as elastic links between coincident nodes, allowing the simulation of swell behavior. And then the other thing that is what we will be doing is a slab on an elastic foundation. It actually simulates a concrete slab supported by a compressible swell. This is particularly useful for modeling a raft foundation, either surface beds or ground slabs. And then within Prokon frame analysis, such models use shell elements for the slab, or to actually build your slab. And then from there, we use spring elements to actually represent the soil stiffness underneath or beneath the slab. And like I said, the first thing that we're going to do is us creating nodes um, in frame analysis. But firstly, in terms of nodes, when we have spring elements, so spring elements are defined between two nodes that are coincident, meaning the the nodes that you create for spring elements as well as your substructure, they have to have the same coordinate in space, meaning you model two separate nodes, or two separate uh, nodes, and then they are coincident, and then you are they are on the same coordinates as each other for the slab as well as for the support that you will provide, and in between you will have that spring element in them. And then the second thing is, when you are creating nodes, you need to create an additional node that will be used to define the orientation of your spring elements. So you need to create, or you need to give an arbitrary node number that is assigned to that specific node. It can be a node number that is not within the range that you have used for all the nodes that you have created for your model. So if you look at this picture, what I'm trying to explain is you will have two sets of coordinates, which is the bottom one and the top one. So that the second coincident node, you will use it to define your, either it is your beam that you are trying to analyze or design, or a slab. And then at the bottom will be the nodes that you would use for your support. And then in between these two nodes, there will be a spring element, which is what we will definitely define as we proceed. And then lastly will be an additional node, which is your orientation node, which is that one there in this picture is node 100, and then it is an additional node that will be used to define the orientation of your spring elements. And without wasting any time, I am going to open frame analysis so that we can simply start modeling. So the first thing, like I mentioned, we will start creating nodes. So we will start with node 1, and both in the X, Y, and Z direction, I will make that 0, 0. And from there, what I'll do is I'll create extra nodes, and I'll say 10 extra nodes, and node increment will be 1. And I'll space these nodes at 0.3 meters in between each other, right? And then from there, to actually define my slab, I will create extra rows in the Z direction, and I will use the block copy function. So hyphen, and let's have 10 extra rows. And the last node was node 11, so the next node will definitely be node 12. So the node increment should be 11 for the next node at this point there. And then, like I said, I will space them 0.3 in the Z direction. And just like that, we have defined the first set of coordinates for our model. Then to create the second set of coordinates for our model, we will definitely use the block copy function as well. So we will block copy line 1 and 2. And how you know what line this is, at the bottom of your screen, it will definitely show you line 1. And if I select that one, it will definitely show line 2. So we are going to go block copy line 1, 2, 2. And remember, we only need one copy. And from there, I can see the last node that was created was 121. So the next node at this point should be 122. So the node increment will definitely be 121. So we have created a coincident nodes, which is for our slab, and then from there for our support, and for the link between the two nodes to create the spring elements. And the last node that we will create will be the orientation node, and I'm going to make it node 1000. And in the X direction, I'm going to say 0, Y direction 1, and then 0 in the Z direction. So if you look at the model, that is where our orientation node will definitely be, right? And then the next step, or the next thing we will definitely do, is we will create a shell element. So if I move from the nodes tab to the shell tab, and firstly we need to define our shell, and from what we are going to do is we are going to definitely use the second set of node of the coincident nodes to define our slab. So the first node that we're going to use will be 122, which is the one at that corner. So how, or the sequence in which we define our shells is, you can either go anti-clockwise or clockwise. That is all dependent in you, but in my case, what I'll do is I'll define the perimeter of my shell going in that direction, meaning I'll go from node 122, and then from here it will be 133. If I zoom in, that it should be correct, 133, and the next node will be 134. And the moment I start populating each node to define my shell, you will see on the screen the shell will then be populated, and the last node to close off my shell will be 123, right? And then for number of extra, so I'll copy this shell in the Z direction. So I will have how many copies? 1, 2, 3, 4, 5, 6, 7, 8, 9 extra, and the node increment should be 1. And I'm going to make this shell definitely, or the thickness of the slab to be 0.3. And then in terms of material, I will use concrete 30 MPa. We can definitely use 40 MPa, but this is just for today and for modeling practices for today's webinar. So now what we can then do for the next step is we are going to copy over these shells to these rows, and we can definitely use the block copy function. So B1, and we need 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9, and number of extra, it should be 11. And from there we have our shell definitely created, right? And then from there, from there, once you have created your shells, the next step will definitely be creating your spring elements. And there are different things that we need to consider, and that is your spring stiffness that we need to calculate. And I'll definitely go back to my slides or to my presentation and just go through that. So when defining spring elements or spring element definition, so the inputs for your spring element is similarly to how one would define your beam elements, or it is similarly to how beam elements are entered. So firstly, you need to specify your spring nodes, the orientation nodes, as well as the spring type, and then you need to indicate the spring constant, which is you enter the translation stiffness in the relative direction. And then in our case, in what we are actually designing or what we are modeling at the moment, we will definitely use kx. And then calculating the spring stiffness, and the spring stiffness is calculated as kx, which is the k soil, which is your bulk modulus, or your foundation your soil modulus, your soil bulk modulus, multiplied by the tributary area. So where your K soil is the bulk modulus, and in this exercise, or in this case, we will use the bulk modulus of 5,000 kilonewton per meter cubed. And then the tributary area, it is an area influence around the spring nodes that we will have within our model. And the tributary area is defined as, so for this specific model that we're doing, we will have three different spring types. So spring type 1, 2, and 3. So spring type 1 will be the corner, what we call the inner coordinate, which we will be 300 by 300, the area for it. And then the second one will definitely be our corner notes, where the area for that specific corner notes will be 1/4 of this inner coordinate. And then the third stiffness type, or the third spring type, will be the one at the edge, where it'll be half of the inner coordinate. And if I move to the next screen, or the next tab, you will definitely see how I calculated the spring stiffness for each spring element, which is spring 1, spring 2, and 3. So like I said, for inner notes, the area will be 0.3 by 0.3, which will give us 0.9 meters squared. And then the stiffness will definitely be the bulk modulus multiplied by the area, and it will give us 450 kilonewton per meter. And then for our corner notes, it will be, like I said, the area will be 1/4 of the inner note. And then from there, the spring stiffness will definitely be 5,000 multiplied by this area. And then for our edge nodes, definitely the area will be half of this specific area, and it gives us a stiffness of 225 kilonewtons. So now we go back to frame, and we start defining our spring element. So we start with S1. Like I mentioned, we will have three: S1, S2, and then the last one will be S3. And this one is 450 kilonewton, and this one is 112.5, as we calculated on that. And then the last one will be 225. Right, now we start defining our spring elements. So firstly, the spring note, we will have the first spring note will be at this note there, so between node 1 to 122. And then remember, we said our orientation node will be between node 1 to 1000. And what I'll do is I'll copy over this, because this also is a corner spring type. So I'll have one extra, and the difference between that node, so that is 11, that is 1, so node increment should be 10. And I can drop down and select that is definitely spring type number 2. And then from there, it is B1. So we're going to block copy these two nodes to these two edge nodes. So we're going to use the block copy. So block copy line 1, and that is 1. And then the difference should be 110, and that is S2. So you see, now that is being copied over, and then we are going to create for the edge nodes. So from this one, it is 12 to 123, and we need, sorry, I need to make sure I am doing the right thing. So let's say 202, which is this one. Let's create this one, sorry about that. And we're gonna have 1, 2, 3, 4, 5, 6, 7, 8 extra, so 8. And node increment should be 1, and then that should be S3 as the spring type. And then we're gonna block copy these. So we're gonna block copy line 3, and we're gonna copy these over this side of the slab. So that would be 1 extra and 110 as well, and that will still be S3. And then let's create over there. Now that is when we do create that, so it will be 12 and 133. So that point node there, and I need 8 extra as well. And then node increment should be 11, and then that is S3 as well. Now we're going to block copy line, that's line 5, and we're copying this spring elements to this side of the slab. So let's just say one copy, and then that should be 10 increment, and that is S. So now we are done defining all the edge spring elements, and then lastly we will define the inner ones. So this is 13 to 134. So from node between node 13 and 134, and node increment 1 2. How many more extra node? 1 2 3 4 5 6 7 8. So still 8, and node increment should be 1 because I can see that's 134 5 6, so that is why, and that will be spring type S1, which is the full 1 or the inner node. And then lastly block copy line 7, and node increment should be 8 rows going that direction, and node increment should be 11, and that should be S1. Right, so that looks quite nice, and we can see we don't have any errors at the moment, but yeah, that is quite good. So the next thing, or the next step we're going to do in this guideline to actually modeling your spring elements, we need to add in support to provide lateral stability in our model. So for this we are going to definitely use the bottom coincident nodes, which is from node 1 up until node 121. So I am going to add fixity only in translation, meaning in the X, Y, and Z direction, and I will need 120 extra, and node increment should be 1. Right, so we have a complete model, and then from there, the next step from support, let's add in loads, or a load into our model, and that is going to be surface loads, and I'm going to say that load is dead load, and I'm only going to apply it in the middle shells, or only on the middle shells. So what I'm going to do is I'm going to switch on my shell, or shell number, so that I can see exactly where I want to see. I think that should be my middle node there. So I'm going to apply the dead load on shell 50, 51, 60, and then 59. So over there, shell number 50, comma, I said 51, comma, and then I think I said 60 and 59, and the direction should be Y, and I'm going to apply a UDL of 100 kilonewton per meter squared, right? Not we don't necessarily have to this is just for modeling purposes, or for this specific webinar. You can apply the load throughout the slab, but let's just do a case where we just applied the load just in the middle, or on the four middle shells, right? And I just noticed we haven't saved our model, so I'm just gonna save it anyway. Really, I'm just gonna save it to my desktop for now. I'm going to say webinar, right? And then save. And from there, I'm not gonna add in any load combination. There is no particular reason why I'm not doing that. You can definitely add in the different load combination, be it dead load only, and if you wanted to apply live load, you could have done that. But this, remember, this is just guide or for today's webinar. I'm just doing a step by step guidance on how to model your spring elements within Prokon frame, right? And then from there we go to settings, and under settings I am just going to choose my domain as full 3D, and for analysis type I'm going to run a linear analysis. And then you can definitely switch on that it does perform concrete design, but once you do that you need to make sure you also um, look or make changes to the different concrete design parameters that you have within frame. And for that we are going to do or change the concrete cube strength to 30 MPa, and then the reinforcement yield strength FY we will definitely leave it as 450 MPa, and then the angle between local axis and the main rebar axis, it is 90, and then the angle between local x for the rebar and the secondary rebar, which is the y-axis, it is 90. And then I will leave the cover as it is, as we see it at the moment, and then I will add plane stress. I will leave it as yes, and then please make sure you select the right design code, which is sub 000/2000, and then select the available load case. And once you're happy with these concrete design parameters, we definitely click OK. And let me just go back to inputs. Under general, let's make sure under add own weight to load cases we can add the own weight to, or the self weight to, the dead load case. And from there we can simply switch to our analysis tab, and I am definitely gonna run analysis. And from what I see, we have run a successful analysis without any errors, and I can definitely see that the maximum deflection for the load case that we actually did, or I applied onto the slab, is 2.33 millimeters at node 182, and I think it is in the middle of the slab. And let's just switch to there, and I have a feeling from what I'm seeing, the deflection seem or might look like it is uniform throughout the slab at the moment, or based on the results that I am seeing here. But we can definitely go to the output file, and then we can check under nodal displacement. I am just going to scroll down, and let's just check under Y from node 123. You will see that's when the deflection will start showing, and you will see it is 2.26, 2.27, 2. So that is why I say, based on how I modeled uh, the slab and the spring elements, it does look like the deflection is uniform throughout the slab. And then from there what you can do is we can simply switch to the reactions and actually see the reactions that we have within in our results tab, and you will see that we do have Y reactions, and you will see that they are actually uniform as well on the edges as well as in the middle if you look closely, and that is quite nice. And then the next thing that you will definitely want to see will be the stresses, and if you look at the one mass stress, you will see that the maximum stress is 434.7 kilonewton per meter squared, which is in the middle of the slab. And then the other thing that you will want to check out will be your moments in the y direction. So we go to moments and forces, and then we change the bending moment type to moment in the y direction, and you will see that the moment is quite small, 6.5 kilonewton meter per meter. And the other thing is, if you are looking into getting or designing getting the reinforcement for the slab, you will definitely switch to your shell reinforcement, and from there you will be able to pick up the rebar, as well as be able to see your wooden armor moments on the slab as well, in both the top in the X and Y direction, and the bottom as well as in the X and Y direction. This is quite nice. Remember, this is just a guidance on how to model your shell element, your spring elements in Prokon frame. And before I get into more details, or um, before I actually let you guys have any other questions, I want to do something quite nice. I am going to try and model the same um, slab or the same scenario in Prokon Sumo, so that I can show you guys that we can definitely do the same thing that we just did in frame, but in Sumo would be quite faster, and but we will definitely yield the same results in terms of deflection and all the other information. So without wasting time, I am going to launch Sumo so that we are able to go through that process as well. So with opening just a Sumo or Sumo, a Sumo interface or Sumo analysis tool, it is the same as frame, but the difference between the two is the modeling philosophy. But I'm not going to waste time explaining the difference between the two models. I am just going to go straight away and try and model the same thing that we just did in frame. Now, the first thing that you need to do is definitely import material that we need to use for this specific slab. So we will use a 30 MPa similar to what we used in frame. So 30 MPa, then okay. And then from there we will start under the structures tab and surface. We will definitely select that we do want to add in our slab. And if we move to the right hand side where we have our properties palette, we can definitely edit those before we can apply or add or place our slab in our modeling space. Now, we made our slab 300 millimeters thick in frame, and we are definitely going to make our mesh size 0.3. Remember, we made our spacing between our nodes in frame to be 0.3, so we will definitely do the same here, so that we see if we will definitely get the same results. And then make sure that the material that you want to use is the 30 MPa material, right? And then I'm just gonna switch on the grid snapping on so that I can start modeling from the 00 coordinates, and then from there press tab to highlight our polar dimension, and I'm going to model a 3x3 slab, which is what we definitely did in frame as well. And then 3, press enter, and there press escape, and then I'm going to create another line going in this direction, tab 3, enter, right? And I'm going to select this, copy. I'm going to copy it from that point to there, and then copy this line as well to there. And once we are happy with our slab, we can accept so that we place our slab. So that is what we have, a 3x3 meter. We can definitely use this to check that we definitely have modeled a 3x3 slab. Let's just do that again. Hover over at this point, that's 3, and then from that point to there, that is 3. Right, press escape. Now the next thing that we are going to do is we are going to apply an area support, where we need to indicate the soil underneath the slab, and we'll definitely put in or indicate the sub modulus or the subgrade modulus, the same one that we used in frame, which is 5,000 kilonewton per cube meter. And we are going to definitely add or place that all round of the slab we just defined. Accept. And then from there we are going to definitely add in support for stability, and we are going to make only the y direction free, and let's add one support in each corners of the slab, that is. And then we'll press escape. And the next thing is, remember we had a load case, so in Sumo we'll go to the load case tab, and we're going to add in a load case. And then under the messages, you can see automatically calculated self weight. We are going to add in the self weight to the dead load. And if I would, I'm just going to select the slab and mesh it, and then switch to the discretized model. If we look at this, if I count these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, definitely we have 10 shell elements in the horizontal direction as well as the vertical direction, because we have spaced, or the mesh size is definitely the same as how much we spaced our nodes in frame as well, right? And then from there, what we can definitely do is we can apply that load that we applied in the middle of our slab, similarly to what we did in frame. So what I'm going to do is I'm going to switch to top view, and let me just select this. I hope I'm selecting the right thing. Let me just filter, and I want to select only the slab. I want to change the capacity to 0.5 so that I can see exactly what I am doing. I can be on analytic, under the analytic model. That's fine. So before I can do anything, what I will do is, because I know I want to create or I want to apply that load in the middle of the slab, I need to use, I'm going to use lines or curves in order to define where I will place my aerial load. So I will just go back to my analytic model, and I'll insert a curve, and I am gonna define the coordinates where I want to start applying my nodes. Let me just start that again. So if I go back to insert curve, and I want to start from 1.2 in the x direction, then 0 y direction, and then 1.2 in the z direction. If I press enter, you will see if I move my mouse, it will show me that is where I'm beginning, where I want to place my aerial load. So then I'll press tab, and it should be 0.6, because the two shells that I have applied the load onto, the other one is 0.3, the other one is 0.3. That is why we're going with 0.6. And tab, and I want to make my angle 0, and you will see that line defined. I will define the one in the vertical direction, tab, that should be 0.6. Tab, the angle should be 0. Right, and I can simply select this, copy there, escape, select this, and then copy from that point to that point. And then from there I can definitely go to loads, and then area loads, and I will apply 100 kilonewton per meter squared load, and then the direction will definitely be y, and then lowercase will be LC, and then the load will start from that point to there, there, and there, and there. Once you're done, you click accept, and from there we can switch to our isometric view, where we can see our complete model, and you will see the 100 kilonewton load applied in the middle, similarly to what we initially did in frame. And then from there, I think we need to save this as well. So save as, so I'm just gonna say webinar and say save, sorry. And then from there we go to our analysis tab, and we can click on settings. We will definitely run just a normal linear analysis as well for this, nothing fancy, because we are just trying to see if we will definitely get that. Once you have run a successful analysis, there will be no messages under the message tab, and definitely your results tab will no longer be grayed out. Then we can simply view our results, and you can see from the top right hand corner, you will see that the displacement or the nodal displacement is similar to what we initially got in frame. I'm just going to open that frame model and go back there. It is minus 2.33 millimeters at node 182. And if I go back to Sumo, you will see that as well. I am just gonna switch to my top view, and what's nice about Sumo is if you hover over each node, you will see the displacement for each node, and you'll definitely be able to see that the displacement is definitely in the center, similarly to how we saw it in frame. And what's nice about Sumo is if I switch to the front view, and I'm just going to leave the multiply as it is, and if I click on animate, you will see exactly how this is deflecting, which is quite nice. And like I said earlier on, we will see if that the slab is or the deflection for the slab is uniform throughout, even though if we go back to the top view and hover over, you will see that the displacement increase uniformly as we go into the slab, in the middle of the slab. And then the next thing that we will definitely be able to see will be the reactions. And let me just switch to isometric view, and you will see the different reactions for the different uh, the different reactions for the different vertical reactions. Because remember, with aerial loads, you will get reactions at every or for slab, or for for your slab, your reactions will be determined, or if you have an aerial support, your reactions will be determined by the mesh size. So if it's 0.3, you will see the reactions at every 0.3 meters, which is what we are seeing. And I think it's quite similar to the reactions that we got in frame, and I can simply switch to there as well. Yeah, that is definitely right. Yes, we are getting the same thing. And then from there, we will definitely switch to your shell. If I go to plate and go to moment in the y direction, you will see that the moment is actually the same. It is 6.521 meters. If I go back to frame as well, that is what I definitely did get. It is 6.5 kilonewton meter per meter, which is quite nice. That you can definitely model this in Sumo as well, and it doesn't take quite a long time, and you will definitely get the same results, or more or less similar to what you have yield. And you will see that the reinforcement the area of still in the x direction at the top, and then the area of still in the y direction at the top, and then the area of still in the y direction at the bottom. It will definitely give you the same thing. Even if I go back here and I go to shell reinforcement, and let's switch to y bottom, and you will see 6.5. Well, that's the moment with an armor moment, sorry. Yes, this one says 73.1, and I think the other one says 66.01. That is fairly not far from each other, but in terms of deflection and all the other reactions, basically it actually was basically the same. So that is an nutshell of what you can actually do in frame as well and as in Sumo. What you actually did in Sumo in frame can take a smaller time or smaller amount of time in Sumo. So that is quite good. What I just did on frame is exactly what I did now in Sumo, and that is an in a nutshell what or how you model in your spring elements in Sumo. And I think we are now good with questions. I don't see any questions in the chat box, but I'll definitely just stick around for 5 more minutes just so that we go through any questions if anyone has any question for us. But I see there isn't nothing, but that is basically it. I know I wasn't really comparing the two, but that is how you create spring elements or foundation, or indicate how you add in spring elements when you have slab and you want to indicate or see the soil beneath that specific slab. So any questions? I don't see any questions on the chats at the moment, but I will definitely wait if anyone has any question for us today. I see there is a few questions. Okay, the other one says, "Hey, thanks for the presentation. Thank you so much. Thank you. I appreciate it. I'm grateful that it was insightful for you, and thank you for joining me." And then it says, stiffened raft foundation with downwards beam. Is it possible? Uh, I I stand to be corrected by the, but I think that is something that we can try and do. But I have never tried it in myself. But I think what I can do is I can try and do it, and then we can see if that is possible. Yes, you can also analyze it if the beam is also resting on elastic support. Yes, you can do it for both when it's a beam and a slab. So you can do it with both scenarios, JP. That's, yeah, that's possible. I hope I answered your question, Paul, but that's what I think. I haven't really tried it myself with a downwards beam, and I'm not sure if it's possible, but it's worth us trying if it will be possible. So that is something that I can try, and then I can feedback on that. So you can definitely send me an email once we are done, and then I can definitely see if that is possible. I've never tried it myself, but I mean, it's something worth a try, and yeah. That's all I can say for now. Oh, JP, you said hi. Thanks for the presentation. How would you model the change if I want to put a beam around the edge for, it says, how would the model change if I want to put in a beam around the edges? So I think also, even if you have a beam around the edges of the slab, you can simply add in the so how it would change is um, you would have the spring element between the beam, so it will be the beam and the spring elements on the edges, and then inside the slab you will have the spring elements connected to the slab. So that's how the difference would be. On the sides, the spring elements will be connected to the beam, and then in the middle where you have the slab, then the spring elements will be connected to the slab. I think that's, well, that will be the difference, because at the moment we have the slab all around, and then we have the spring elements throughout the slab. But if you put in an edge beam on the sides, then the spring elements will be connected to the beam, the beams, and then you will have other ones inside where they will connect with the slab. But just make sure that there is a connection between the outside beams and the slab as well. All right, I think those are all the questions that we had, guys. If I haven't answered your question, or you still want more clarity on your questions, please, please, please feel free to contact us or contact myself. My email, oh, I see Paul. Yeah, basically say, okay, I've never done it where we have a downstand beam, but I think it's something that I need to actually do in order for me to actually advise on that. So I think, let me try that, and then I will definitely get back to you, Paul and JP, and then I will definitely advise on that, more on it. But I've never tried it myself, and yeah, that is what I will say. I've never tried it with a downstand beam on the edges of the slab, but that is something worth a try, and then I will definitely uh, you can definitely send me an email, and then I will definitely see if I can be able to do something like that, and advise better on it. So you guys can definitely email me at mj@mgfx.co.za, or you can simply email on the email address that you're seeing on the screen right now, which is info@mgfx.co.za. And you guys can definitely um, go to our website for all the content that we have, which is www.mgfx.co.za. And thank you so much, guys, for watching. If there's basically more questions for me, please, please, please feel free to send us an email. And thank you so much for watching, and please like and subscribe for our channel, and then we will touch base whenever you do send an email to us. Thank you so much for joining me, guys. If there are no other questions, I'm just gonna sit and wait if there isn't if there are more questions for me for today. But thank you so much for joining me.